All right, welcome to lecture 19, CS 194. We're going to talk today about sparse matrix vector multiplication, and we'll talk a little bit about why it's an important computational kernel. That comes up a lot. Thank you for the good morning. Let's see. So I'm going to do, let's see, I wanted to start by just having a little bit of let me see, I'm having trouble getting my slide to advance there. Okay, a couple of announcements. We're not going to have lecture on Wednesday. I had originally planned to have a sort of optional lecture, and I may record something that you can listen to asynchronously, but at the moment, given everything that's going on here with the election and things, I think that we could all use the morning off. So that's the plan for Wednesday. I do have my office hours. Not too many people come. I guess some of you have been there that I see here online. They're at noon on Fridays. And by the way, if you're interested in talking about other things such as research or whatever, you're welcome to come to my office hours. You're also welcome to post me privately on Piazza, or post Ben and me. And Ben works in my research group as well. So we can certainly give you advice on that as well. And this has come up, and I think there are a number of interesting things that could be done, for example, in GPU programming and related to sparse matrix vector multiply and other sorts of graph algorithms and things like that, other sparse matrix algorithms as well. We will be releasing homework 8 soon, so that you can work on it during the weekend, next weekend. Okay. I'm using a bunch of slides from a whole bunch of different people in addition to my own, some of them borrowed from me, and now I'm borrowing back from them, and so on. Okay, so this is in the middle of the GPU unit, and it will seem like not so much of a GPU related lecture. I'm going to talk about, I've been talking in the past couple of lectures about data parallel algorithms, things like scans, and that's what you're working on in the homework. And part of what I want to get to is how to do sparse matrix vector multiply on GPUs, including using segmented scans. So this sort of top piece is the high level picture of how this lecture fits into what we've been talking about. But in order to do this, because we haven't talked about sparse matrix vector multiply, I'm first going to talk about dense matrix vector multiply, which you've certainly seen a lot in lab and homeworks and things like that, as well as dense matrix multiply. By the way, DGEM with an M on it, so 2 M's on it, is the LAPACK, which is one of the standard library for linear algebra. It's named for dense matrix multiply, and this is DGEM-V is the name for dense matrix vector multiply. Okay, I'll talk about sparse matrices. We actually won't have a chance really to talk about register blocking today, I think, so much, because I want to make sure we get to the point of talking about GPUs. And that may be what my extra lecture is on, but it won't be really part of this, or I'll give it next week after the quiz. Okay, next Monday, by the way, will be a review also for the quiz, as will lab this week. Okay. So parallel matrix vector product, which you've seen many times, but I just want to remind you, I think mostly you've been looking at it as an algorithm based on dot product, and you've looked at how to parallelize it in things like OpenMP. And so you can think about this as dividing up the matrix in rows. And by the way, when we start the next unit, in the last unit, unit 4, we'll really be thinking about partitioning the matrix, that is giving each processor its own block of rows that other processors don't have. But for now, you can think of this as just logically the piece of the matrix A that each one of the processors is going to sort of own. It'll be probably in their cache at some point in this algorithm. And so this is a row blocked layout. I'm trying to remember whether you actually did a row blocked layout or just a row cyclic layout, that is just mapping the rows one at a time around the different processors. And in the particular lab, I know you looked at blocking and things like that at various points. So the algorithm then is just computing this operation AX times Y locally on each one of the processors. Let me just see if I've messed. So this is doing each processor then has to get all of the elements of the source vector, and they can do these local computations then on the matrix X and update independently this piece of Y. And this is really actually a dot product algorithm. Okay, and this is more of what's called a DAXP algorithm, and I've flipped the two labels here. So what happens in the opposite, if I have a column block layout of this, is that each processor owns some piece of the X vector and the corresponding columns of the matrix, and you multiply those down. So think of it as broadcasting down, but there's nothing to broadcast because the processor owns it all. And then, but you need to then do a parallel dot product across the different rows because each processor doesn't own a complete row, and update the Y vector as well. And so this is a reduction, and so the code here is correct. It's doing a sum reduction across these different values. Okay. So you've seen both, hopefully you've seen both of those, but you've certainly seen one of the dimensions, I think the dot product one. And we can also do what's called a two-dimensional layout, that is divide the matrix up into these separate blocks so that in 2 dimensions, so that we use, for example, 16 processors rather than just 4 processors in this particular case. And then what you end up doing is both a parallel broadcast across the rows, the block rows. So say this first little piece of the green input matrix would be broadcast down to P0, P4, P8, and P12. And then the multiplications would be done by all the elements in there. And then there would be a dot product or a sum reduction across the block row. Okay, so this is sort of somewhere in between the column layout and the row layout. All right, so that's dense matrices. You've worked with them a lot, so I think you're familiar with them, but I just wanted to start with that because it's the easy case, and we can see how things get more complicated than when the matrices are sparse. So this is a nice quote from somebody from Harry Markowitz, who won the Nobel Prize in economics of all things. And he started actually in a job at Rand Corporation in the 1950s. And what he said was that the models they were using, so they were using industrial simulation sort of models, and the models were straining the computers of the day. Now, you can imagine that those computers in the 1950s were not very fast by today's standards, but they observed that most of the coefficients of the matrices were 0. That is, the matrices the non-zeros were very sparsely distributed throughout the matrix. And he and his team then, and he credits a number of other people who actually built a number of different algorithms based on taking advantage of the sparsity of the matrix. So what is a sparse matrix? It's a matrix in which most of the entries are 0. Typically in large, if you've got large matrices, a sparse matrix, and we'll be looking at really small matrices in this lecture, but in an actual sparse matrix computational problem, especially one that's running on a parallel machine, whether it's a GPU or an SMP or a distributed memory multiprocessor, well over 90% of the non-zeros will be, of the entries on the matrix will be non-zero. And so over 90% will be zeros. Actually, typical percentages of non-zeros might be even 0.01%. So really well below a single percent. But most of them are zeros. So rather than representing them as dense matrices where you're wasting all of this white space by putting zeros into the matrix, and you're also going to waste computation by multiplying a whole bunch of zeros, you're going to just compress them and only store the non-zero elements, but then you have to keep track of where those non-zeros lived in the original matrix structure. And they come up all over the place in applications. I'll give it some more examples of them in a few slides, but simulating climate change, analyzing images, web ranking, graph neural nets, which are a form of machine learning, and other graph computations. So mathematically, a sparse matrix and a dense matrix, the corresponding matrices are exactly the same mathematically in terms of what you're doing. You're multiplying by a bunch of zeros versus not actually storing those zeros. But in terms of what it looks like from a computational standpoint, how you optimize it for a parallel machine or even for a memory hierarchy is going to be quite different. So if you consider this really simple sparse matrix, which is a diagonal matrix, So this is really the simplest of all possible sparse matrices. There's only one non-zero per row in here, the orange elements of this matrix. So don't think of these as blocks. Think of these as individual elements. And if you're going to perform a matrix vector multiplication on this, well, in this dense format where all these white zeros are filled in as zeros, you're going to do 2n flops, right? You'll do a multiply and add for every element of this matrix. In the sparse representation, because there's just n of these non-zeros, and each one of them you just have to multiply and then add the result matrix. And in the dense representation, if you do all of the multiplications on the zeros, you're going to actually do 2n squared. And a lot of them will be multiplying and adding zeros. Okay, so here's some examples of structures that come up in sparse matrices. So you can have, so the diagonal one that I just looked at, tridiagonal is also quite common. This comes up if you have sort of nearest neighbor computation on a one-dimensional mesh. You can also have a pentadiagonal. That would be nearest neighbor computation on a two-dimensional mesh. It would come up in things like convolutions. But if you think of that operation as a matrix, then it turns into one of these types of diagonals. You can have more general, sort of generalized diagonal formats that come up in various computational problems, depending on sort of how far away the effects of something are having on a particular, say, a simulation problem, if you're looking at, the heat dissipation, for example, or something like that. In the bottom, we have things like dense block matrices. So they have little dense blocks in them. That will be especially important optimization when we look at optimizing for memory hierarchies, which I'll probably talk about in a future lecture, not so much today. Symmetric matrices also come up a lot. And if you've got a symmetric matrix and it has both symmetric, some of them are just symmetric in their structure, but may have different values, that the orange values may be different above and below the diagonal. But if everything is symmetric, the values as well as the non-zero structure, then you can just store half of the matrix, where half means including the diagonal. So not exactly half, but. And you can have completely arbitrary sparse matrices. And these come up in certain types of graph problems that when we're trying to understand connectivity of things. So we'll look at that. So here's a matrix that you see every day. Any guess as to what this matrix is without looking ahead in the slides? So this is actually the web connectivity matrix. And people analyze this quite a bit for a number of different reasons. One of the reasons they look at it is to try to figure out which websites are more important. And this is, so this is looking at what websites point to what other websites, for example. So this is what the graph looks like for internet connectivity, this orange blob here on the left. And this matrix then has some structure to it. You can see there's some kind of blocking structure around the diagonals. Why would that be? That's because especially if you've ordered the matrix in the right way, if you've got, for example, all of the websites at Berkeley, they're going to be one of these kind of dense looking blocks, and that there's a lot of pointers between websites at Berkeley to other websites in Berkeley. And you'll have other clusters like that are relatively dense with a lot of pointers between them. And the second one is on structural design, and that this graph here, this grid structure is turns into this sparse matrix structure. So the way to think of this is when I'm going to multiply this matrix, it's like doing nearest neighbor computation on this graph or this mesh. And so that's a really common thing to want to do, whether you're solving PDEs or you're trying to understand something like the page rank of what is the most important page on the internet, and linear programming, which is more of an optimization problem, might look something more like the one on the right. So what does the diagonal represent here? So the diagonal represents kind of self pointers to a vertex in the graph. So the diagonal typically in a lot of matrices is going to be non-zero, because every vertex in the graph sort of depends on itself. And so if you're going to multiply that, you want to make sure that you're using that value, although we'll look at some examples that don't have a non-zero on all the diagonals, just for when we look at these really tiny examples. But the diagonal, so I guess maybe the thing that I should say is in the matrix structure here, So if we look at something like this internet graph on the left, every, say, web page is a different row and a different, and in the same order, a different column of this matrix. And we put a non-zero in here if there is a link from the website on the left, you know, in the column to the website, in the website, and in the row to the website in the column. And so you sort of, every website kind of points to itself in a certain way, or at least that would be a common way to think about it, is that every website's related to itself and then related to some other websites. Does that answer the question? Okay. So this is the linear programming matrix, drawn out a little bit more. So why is it got such an odd shape? So not all sparse matrices are necessarily square. This would be looking at something like a whole bunch of variables that you're trying to optimize for, and then you have some constraints that are on the number of rows. If you're looking at something like a recommendation system, so you're trying to understand what books do various people want to read, or what books would they like based on what books they've already read and have ranked highly. You start out with a sparse matrix, which is you have a certain set of individuals, which are the rows of the matrix, and say a certain set of books or movies or whatever it is, shopping, you know, items you can buy on Amazon or whatever. And you put in their ratings that you have, but for any given person, you don't have a dense set of all of their ratings for everything that's in the, you know, that's on the internet, every book, for example. But you'll have some people that have read each book, and you can get their ratings from it. And so you'll use this matrix and analyze this matrix to try to figure out what is the likely rating for the ones that are missing. It comes up in things like image segmentation. So you're trying to identify the objects. So this picture on the left turns into this sparse matrix in the middle, and you actually compute the eigenvectors of this. So you should have learned about that in your linear algebra class, whichever one you took. And this will give you the outlines here of the different objects in the original picture. But you perform that eigenvalue computation then on the sparse matrix. So I mentioned Google's PageRank algorithm was originally at least done with an eigenvalue computation. You can look at transportation networks to understand the severity of different types of cutting of the transportation network. If there's some kind of a traffic jam on part of it, things like that. You can use it for textual analysis, trying to understand how different terminology, different words in text are related to other words. And in scientific and engineering applications, I've mentioned both solving differential equations, so things like climate modeling, materials modeling, fluid dynamics of other kinds, you know, and simulating engines, simulating lots of different things, structures, earthquake simulations, as well as optimization problems where you're trying to design something. Okay, so now a little flashback to 61B. I stole this from Paul Hilfinger's slides for graphs and 61B, because graphs and sparse matrices are so closely related, you really want to be able to go back and forth between the two of them. And since I know you're more familiar with graphs from 61B, I wanted to just remind you of what they look like. So it's got a number of nodes or vertices, as they're called. So those are synonyms, and the number of edges that connect them. So here's an edge list representation that gives each node, and it contains some kind of a list, such as a linked list or an array of all of the other vertices, all the other nodes that it is connected to. So in this little tiny graph, A is connected to B and C. So A has this a pointer here to the 2 and the 3. B only points to the 3, the C in here, and then node 3 has a C label, and it points back to it doesn't have any next pointers. So the first field in here is the next pointers, kind of the things that it's pointing to, and then the second pointer inside of there is the things that point to it. And you can also do this as an edge set, a set of all of the edges that are in the graph. So notice this doesn't have the values A, B, and C in here, but it says what the structure of the graph is. the different edges in it. And you can also turn this then into an adjacency matrix. And so here's where we get to the idea of the matrix. So the matrix representation says 1 is connected to 2, 1 is connected to 3 in the first row, 2 is connected to 3, so B is connected to C, and then 3 doesn't have any outgoing edges, so its row is empty. Its column, on the other hand, has 2 1s in it because it has 2 incoming edges. So that's the, any questions, just kind of reminding you about the adjacency matrix representation, as well as the adjacency list representation, which will give you some kind of a list of the outgoing edges. So in a sparse matrix representation, and specifically a compressed sparse row implementation of a sparse matrix, which is what we'll be focused on today in this lecture, it's really a cache efficient version of an adjacency list. So in 61B, if you worked with adjacency list representations of graphs, you probably had a linked list of all of the outgoing edges. Linked lists are great because you can easily insert and delete from them. So you can modify the graph structure pretty easily. But if you're going to, if you have a fixed graph structure you want to analyze frequently, or a very large graph structure that's going to, you're going to iterate over that graph structure, walk over that graph structure many times, you want something that's more cache efficient than linked lists. And so you'll store the adjacency list as arrays. Here's the adjacency list representation of this particular graph. So this does have linked lists for each one of the vertices in the graph. And then here's a compressed sparse row representation, which is this has the list of values here. So the weights here are the value set, which is the gray row here at the bottom. So 12, 26, 19. So these are all of the different weights of this matrix stored in an order based on which ones are outgoing edges. So the important thing is that the adjacencies then tell you which thing they point to. So in and the input array, the first array here is the row start array in compressed sparse row format. That's the index into the adjacency array where each one of the vertices outgoing edge sets is stored. So for example, vertex 0 goes from 0 up to 1 because the next thing in the adjacency array is a 2. So just looking at this first array and the first 2 elements of it, it starts at 0 and then goes up to 2 minus 1, which is 1. So the first 2 elements here are belong to node 0. One of them is an outgoing edge to itself, so that has an adjacency element of 0. And the other one is to edge number 2, so that has a 2 in there, and then you see the weights underneath at 12 and 26. Okay, this is very important, so I want to make sure people actually understand this. If there's anything you want me to walk through again, please ask. Okay, now we can also look at the adjacency matrix as we saw in the 61B slide. So this would be the adjacency matrix representation of this graph. It's got the edges here. Each one of these rows is dense. That is, it's got a column for every one of the vertices in the matrix, and only the things that have an edge to it are filled in. And so this looks like the matrix that you see here. And so you can also look at this bottom compressed sparse row version of this as taking this matrix and sort of squashing out all of the zeros. And you can see that the weights here are in order. So you've got 12, 26, 19, 14, 7, which is just running across the rows of the adjacency matrix in order. And then remembering which index each one of those elements was in this adjacencies array. Okay, by the way, if we have an undirected graph, we can also store it in these formats. An undirected graph is going to look like a symmetric matrix. So here I've removed all the arrows from this graph edge, and now I've flipped over all of the non-zeros in this adjacency matrix representation. So this matrix is now symmetric in both values and in structure. And I can still use this kind of a compressed representation. I have to know that the matrix is that the matrix is symmetric, that it is undirected, so that I should think of each of these edges as going both directions. And whether that's the best representation for this depends a little bit on what you want to do with it. Okay, so sparse matrix vector multiply. So as I said on a graph, what you should think about this as let me go back to the directed case here, as walking one of the edges, computing a new value for each one of the vertices in the graph based on the old value of the vertex at that position and some weight on the edge, and maybe the weight on the edge of the thing that it points to. So you're going to update, say, the orange vertex based on the blue vertex and itself, and based on these weights 12 and 26. Okay, so now we've got our sparse matrix vector multiply. So what does matrix vector multiply look like? I prefer to write the X vector in matrix vector multiply above the matrix, as I did in the dense case before, because we're going to take each value of X and we're going to need it to compute all of the elements of the column there. So writing it this way helps me think about the communication pattern and what happens when we parallelize this. Now, this is the adjacency, the dense adjacency matrix representation here shown in the picture. And this picture then on the right is the sparse representation of A as we would actually store it. And so we've got a pointer array that has, if we've got M rows in our matrix, we're going to have M plus 1 elements. The extra element in the pointer array is going to be helpful so that we always have the next thing to use when we talk about our running through one of the rows of the matrix. We'll see that in the code. And we have an array of values. So those are the edge weights on the matrix, and the indices, those are the vertex values that are associated with each, with each of the indices. So this is just the matrix. This is the index, so which is the number of the column index of each one of those values in the matrix. Okay, so if we want to do matrix vector multiply, we're computing y sub I is equal to y sub I plus aij times x sub j. All right, so we can certainly do that over here in the dense representation. We talked about that before. What does this look like in the sparse representation? Well, we'll walk through the rows. So this is a serial code. We'll walk through the rows of this, and for each row, then we'll walk through the columns that are non-zero columns. So we'll look at the pointer K starts at say the red pointer, whatever that points to, in this case 0, and then it goes up to the pointer plus I. Whoops, it should say minus, it should say this is not inclusive, so up to but not including pointer I plus 1. And then you do this y sub I equals y sub I plus the value, and then times the x index. So x is this purple vector here shown at the top. What do we have to get out of that x vector? Well, it's whatever column this non-zero is in. So this non-zero is just value of k, right? That is indexing into the right position in the value array. But now we have to get the x value out, and that we have to figure out what column am I logically in this sparse matrix. And so I look at the index value that that k is pointing to, and get that out of the by looking at the index array, looking that up and getting it out of the x vector. So I can parallelize this in OpenMP. Here's one version of the code for OpenMP. There's lots and lots of different ways you might want to optimize this, but basically you can take this code and stick OpenMP pragmas on the outside of it. You can do static scheduling of it, or you can do dynamic scheduling. Any suggestions on why you might want to do dynamic scheduling in this case? Well, the key is to see that the number of different colors in here vary. So we're going to have different row lengths, and so this inner loop at least is going to run for different amounts of time, and for that reason, you may want to use dynamic scheduling because they'll finish at different times. Now, I'm not going to read through this, but here is the well, I guess I'll say a little bit about what's inside of this. This is a sparse matrix vector for a SIMD unit, for an 8-wide SIMD unit. And obviously this code is pretty ugly looking, so that's why I won't read through the details. But basically, we're also going to iterate through all of the rows. So that's the first loop there. The second loop is then iterating for each of the 8 non-zeros. So assuming that there's at least 8 non-zeros in that particular row. And so we're going to pull off a chunk of 8 of those and SIMDize that. And so then the next 3 statements inside of that loop are doing a gather on X. So this Vx is the X vector, and you're looking that up based on the values of the indices, the VLDX, which is getting the indices that correspond to that set of non-zeros. And then you've got the value array, VA, and then you're doing the multiply add. So this is going to be a single multiply add instruction. And this will give you the multiply. But the thing that's slow about this, of course, is this gather operation. So you're going to go and get, say, 8 elements that live at different memory locations and different cache lines and things like that, pull them into your vector register. And then once you've got them in the vector register, things are fast. You can do the corresponding multiplies, just line up with each other. And then you have to do an add in order to get the result of them out. And then you add up and then you also have to worry about the case where the number of columns doesn't divide evenly in the vector width, so there's a little bit of cleanup code. Now, what if we want to write something like this in CUDA? Well, in CUDA, we can do, we can also represent this in CSR format. There are actually other formats that are probably faster, and we'll talk a little bit more about why that is, but it goes to the fact that the row length here is not going to be equal. So if we want to do a sparse matrix vector multiply in CSR format in CUDA, this is a little piece of code for SPMV in this particular case, and we're just going to get our I is going to point into the pointer array once again. So we're dividing the matrix up by rows, by sparse rows, and each then each one of these inner loops, the inner for loop is going to go through that row and do a dot product on that and compute the y sub I value, and then at the end that is written into y sub I. All right, so now to remind you, I think the segmented scans are something that we want to use we can use inside of this matrix, this sparse matrix vector multiply. So we wrote this code, but the problem with this particular way this is written is each one of these rows may have a different length, and they may be fairly short. So you really won't have enough parallelism to keep the GPU fully occupied. And so instead, you may want to do this with something like a segmented scan. People also use segmented scans on other formats besides the CSR format. But just to remind you, in the segmented scan, I think I briefly talked about this, and there's a number of different ways that you can specify these flags. But you have an array of once again, you've got the values, and then you're going to have some way of specifying the flags where each one of the rows starts in the matrix. So there's just a segmented scan operation. So if we kind of walk through what sparse matrix vector multiply looks like using a segmented scan, it actually is doing, it's doing this on once again, the same representation. So we have our pointer array, our index array, and our value array. And what we'll first do is compute a flags array. So flags is equal to a 0 array. And I'm not worrying about, this is pseudocode, and I'm not worrying about the sizes of each one of these vectors, but this has to be equal to the number of non-zeros. And we're going to put then a 1 at every one of the indices in which there is a pointer. So the pointer tells you where each of the rows starts. And so this flags array then has a 1 at each of these locations, which gives us really the split in terms of where are the starts inside of the row starts inside of that. Then we want to compute the x values, find the x values from the x vector here at the top. So it's just I just happened to pick an x vector of alternating 1s and 2s. So all of the values in the x vector, in this x of index, is going to be either a 1 or a 2. So we just look at the index array and look at, say, the first element and the second element. So that's so the ones element is a 2 and the 2's element is a 1. So we get the 2, 1 and the blue first 2 blue locations here. And then the yellow is, sorry, the orange here is the index array has 0, 3, 4. And so we look those up. 0 is a 1, 3 is a 2, and 4 is a 1. So we get 1, 2, 1, and so on through the through the index array. We then compute a product. And so the product is equal to the values array, the corresponding elements of the values array times the X indexed by the index array, what we just computed here. And so in that X of index here, we just multiply this times the value array. So val is the 1, 1, 1, 2, 2, et cetera. And then the X of ind is the 2, 1, 1, 2, 1. And when you multiply those together, hopefully I've done this manually correctly, we get the product array here. So that's the product of those two rows. And then we do a scan on that. And the scan on that is a segmented scan, which is segmented by that, by the thing that we built with the with the segments that were the row starts, where the row starts, which I think I've now lost from my slide, but is the flags array that we computed before. That gives you the starting points for each one of your rows. And so if you do a segmented scan, you'll get a sum of just that segment of elements and then can write that back into the result vector. Okay, questions about that? Okay, now there's a lot of other formats that you can use, and we actually have some extra time here. So I think I might show you some other slides on how we would optimize this for both for SIMD and for registers. But just to finish off, another format that's very popular on GPUs for certain types of matrices is a diagonal format. Actually, this is a good format if you happen to have a matrix that is diagonal. So rather than trying to store this as just a compressed sparse row format, you'll actually store each one of the diagonals contiguously in here. And so in this really perfectly tri-diagonal matrix, this is a great format where we just have 3 rows then stored in the compressed version of it in the diagonal format. We've got the non-zeros here, the red non-zeros, which are above the diagonal, the blue ones that are on the diagonal, and the, I guess, the yellowish ones that seem to have changed color a bit, which is right below the diagonal. And this is the code then that looks at the that operates on this diagonal format. So you can see that it also has it's now treating this matrix as a 2-dimensional array. You have to get the column out of it, and you need to look at the column index that you're storing, the column offset that you're storing in here as well. And we can parallelize this code in OpenMP as well. This is actually can be parallelized on a GPU as well as in OpenMP. And it turns out that probably putting the OpenMP loop, not in the outer loop, but in the inner loop where you're parallelizing over the rows, because you've got a lot of rows in here. You don't really want to parallelize over the diagonals because there's only, say in this case, 3 diagonals. Maybe you've got a pentadiagonal with 5 diagonals, but in any case, you don't typically have that many diagonals where you have very long rows, very long number of non-zeros in your diagonals. By the way, the 2 white squares, just to make it clear, are of course explicitly stored zeros in the matrix. And you can also use this if you don't have a perfectly diagonal format where you've got some number of non-zeros some number of zeros in your diagonals. As long as it's not too large, you'll just go ahead and store it this way and then fill in any of those zeros with an explicit 0. So it's not perfectly compressed, but we have, what's the advantage of this? We have a much smaller index structure than we have in the compressed sparse row format, because in the compressed sparse row format, we stored an integer for every non-zero in the matrix. In addition to the value, we stored an integer, which might be the same size. If we've just got a single precision floating point array, maybe it's half the size if it's a 32-bit int and you're storing double precision floating point numbers that are 64 bits. But in any case, it's a significant amount of storage overhead, whereas the diagonal format is really not as much. Okay, any questions about that? Okay, so I'm going to show a few slides then that I have. Let me just make sure I find the right place in them. And we're going to talk more about how sparse matrix vector multiply gets optimized, because we've done a lot of work on this, and there's, I think, actually some interesting research questions that come up as well. So let me just share my slides. So let me go into display mode. So we're going to look at, this is a common sort of diagonally dominated matrix, but this is blown up from a long ways away. So each one of these little blue blips inside of this matrix is actually a little block structure. So this has, so the dimension of this matrix is 21,000, so 21,200 by 21,200. This is a square matrix. The number of non-zeros in it. So there's on average, I guess about 10 or a little under 10 non-zeros per row. So there's 1.5 million non-zeros. So N and Z is the number of non-zeros throughout the entire matrix, and that's about 1.5 million. And we're going to do sparse matrix vector multiply on this. This particular problem comes from a structural engineering or a structural analysis problem that comes up in NASA. So if we blow this up though, what wasn't obvious from that other picture is that inside of here, you actually have little dense subblocks, and these are 8 by 8 subblocks. And so one of the things that a lot of an engineer might do who's trying to develop a sparse matrix format is say, I'm going to store these as dense 8 by 8 blocks. And that is probably going to be more efficient. Why is it going to be more efficient? Because you're only storing an index. You only need to store a column index and a row index for every 8 rows rather than every individual row. And that really cuts down on your memory space. So you've got 64 elements stored with only two indices, a row and a column index, as opposed to, and actually the row index in a compressed sparse block format is going to be amortized over all the blocks in the row. But in any case, this is much more compressed than storing an index for a column index for every one of the non-zeros in every one of these blocks. So and a lot of problems that come up in practice, especially in scientific simulations, will have a block structure like this. They'll come from finite element problems. You'll end up with little 4 by 4, 3 by 3, 8 by 8 blocks or whatever they are. And since the bottleneck in this, and if we look at the roofline model, this is really going to be limited by the amount of time to read the matrix from slow memory into fast memory on a, say, multi-core processor, on a single processor, or on a GPU, getting that matrix over to the GPU. So anything you can do to compress that matrix typically is going to be a good idea. So as I said, rather than in what's called a register blocked format, rather than storing a non-zero with its own index, we'll store an R by C block. So in the previous example, that would have been, say, an 8 by 8 block with just a single column index. And this means now we're going to change the data structure, and we're going to change then the way the code is written so that it's going to jump over the blocks and then just do a little dense matrix vector multiplying every block. So I haven't written the code out, but hopefully that's obvious what that would look like. A little nested loop that loops there. So it looks like for that previous example that an R and C, that is the register block dimension of 8 by 8, is going to be the best choice. So the question is that actually the best choice? And the answer is, let me just grab my clock so I can watch the time here. It turns out, and this is on a very old processor, so this is results done on a project called OSCE many years ago. So on this processor, the original code with essentially 1 by 1 blocking, that is unblocked code, that has this speed up of 1, and these are in megaflops because this is an old processor, and you can see that the best case performance here is actually a 2 by 4 matrix, which is not obvious from that example, although you can see that a 2 by 4 at least fits inside of the 8 by 8. And the problem is the 8 by 8 is here at a speed up of 1.55 relative to the reference implementation, whereas the other one is a speed up of 4. So any thoughts on why 2 by 4 is probably better than 8 by 8? Where'd my chat go? Well, the answer is because you're going to want to do all of the kinds of optimizations that you did in the first unit, in the first set of homework assignments on matrix multiply, but you're going to want to do things like unroll the inner loop and use register level blocking and things like that. So even though this is matrix vector multiply, you can get SIMDization and things. And so you want to actually not overload the set of registers that are in that little internal matrix vector multiply. So that's why this smaller block size on this particular machine happened to be better. And by the way, on a bunch of other old processors, so you can see this is really out of date. We've got Power 9s today, but this was Power 3 and Power 4. You get different speed up graphs. This is where I think it could be interesting to look at this again on modern processors, as well as GPUs and modern SIMD units. There's some more machines as well. Okay, but a lot of matrices don't have a dense 8x8 block structure like this, what that is just naturally occurs. So here's a fluid dynamics problem. And by the way, problems that come up in, say, analyzing the internet will have even fewer blocks. We saw that a little bit in the pictures, the SPI plots, you saw those matrices before. But let's say that we have this type of matrix that has, you can see the specification. So it's about a 16K by 16K square matrix with 1 million non-zeros total, 1.1 million. So, but if you blow this up, this is what this matrix structure looks like. And so it doesn't look like you can block this very well. The other one had this very natural 8x8 block size, which we used a smaller, version of it, which is the 2x4 matrix block size. But this one is none of these blocks are entirely dense. So what are we going to do? Well, it turns out you can put a little, let's say 3x3 processor grid on it, and or not processor grid, sorry, a matrix blocking grid on top of it. And if we look at this 3x3, a lot of these little 3x3 blocks are either about half full or completely empty. Not entirely true. There's a couple of them that have only maybe 2 non-zeros in it. I think that's the worst one I see here. I don't know that I see any of these little 3x3 blocks with 1, but if there aren't very many of them around. So what we can do then is actually, because we want to take advantage of this register block structure on SIMD units and on just to take advantage of the registers on any kind of a modern CPU processor. And by the way, they also be a good idea on a GPU, although you might use a different shape of blocking. What we'll do is we'll fill in explicit zeros. So this is sort of counterintuitive. In this case, this particular matrix, you actually filled in 50% more zeros than you started out with. So there's half as many of the red dots here, red diamonds here as there are blue diamonds. So I've really added a bunch of extra zeros into this matrix. But now, because I've stored it this way, I can store just one index for every 9 9 kind of logical non-zero elements, the ones I'm explicitly storing. Some of them they happen to be zeros, but I'm going to call them non-zeros because they're going to be filled in as an explicit value and non-zero. So each of these are now stored as a little dense, just 9 numbers in a row. I don't need to store an index for every element. I don't need to remember which ones are 0 and which ones are not, because the ones that are zeros are just zeros. And it turns out that again, on an old processor, but this still is a good idea on modern processors, this was about 50% faster, even when you take into account that you're doing extra work. So the actual wall clock time was 50% faster, even with this, with these register blocking. And now you can look at the roofline plot, and this is, if you look at Sam Williams' PhD thesis, a whole chapter of the thesis is really on sparse matrix vector multiply and how you look at these different processors and try to optimize them for things like adding these different optimizations. So it started out with the unoptimized version that had, and then which was the red triangle here. And then by doing various optimizations, such as making sure that the fused multiply add is actually being used, the register blocking here, which also improves, in addition to giving you a nice little register block, it gives you better instruction level parallelism, data level parallelism, that is SIMD parallelism, a better flop to byte ratio, which might not be entirely obvious from the previous picture, but that matrix that has only one index per block per 3x3 block is actually smaller than the original matrix that had fewer non-zeros stored, but had an index for each one of those non-zero elements. And so it turns out that that's actually gives you a better flop to byte ratio. That's why you can see the roofline graph, the green dot moves a little bit to the right. So I think I will stop there. I think we're out about time. But just that was the main thing that I really wanted to say. You can also try to cache block, although it turns out for sparse matrix vector product, as for dense matrix vector product, you don't have that much reuse. So you typically have a pretty good, other than the only reuse is really the X vector, and that X vector often fits in the cache. So unless your matrix, such as the linear programming matrix, is very, very wide, so your X vector is very, very long, that would be a place where cache blocking might help, but typically it does not. So with that, I will end. And as I mentioned at the beginning, we won't have any lecture on Wednesday, and I will have office hours on Friday. And I'm also happy to talk to people about both quiz preparation, homework 8, which will be coming out soon, and anything else you'd like to talk about, such as research opportunities. Thanks a lot.